I think it quite almost impossible to give a general review of three terrestrial bodies just in 45 minutes of talk. But in any case, I would like to emphasize the major characteristics of their evolution, and that can be seen in their geological maps, and just cite some of the space missions that are planned for their exploration. I think that we all know that from a solar nebula, we had the collapse of the solar nebula into a protoplanetary disk. And from this dust of the planetary disk, we had the formation of, at the beginning, of some protoplanetesimal in terms of 4.5 gigayears ago. And from these protoplanetasimals, you had the formation of all the planetary bodies. And this is what you see actually here. And our attention will be given mainly on bodies that are in the inner part of the solar system, okay? And in particular, it is, our attention it's focusing on the bodies that are closer to the sun and closer to the snow line at 3 astronomical units from the sun, and this is the boundary between the icy rocky bodies and the iron rocky bodies. And all the iron rocky bodies are actually the terrestrial planets, and they are iron rocky because they have are characterized by an iron core and with a plastic at the beginning shell of silicate material and a silicate rigid lithosphere on top of it. And all of them are characterized by this general overview. But the main point here that not all the bodies are of the size. So it means that some of them retained much more energy in their primordial moments. And that's why we have that some of them are still active today, like Venus and the Earth, in terms of volcanism, whereas Mercury and the Moon are not anymore active since more or less 3 gigayears ago. I would say most of their activity ended at 3 gigayears ago. And in the last 50 million years, instead, we have an in-between body, which is Mars, with its own volcanic activity, because it's in between in terms of size. So if we compare the size between these bodies, we have the Earth-like bodies with the surface, if we consider a surface to volume ratio of 1 for these bodies, we have much higher surface to volume ratio for smaller body. And this means that the smaller body have less primordial energy due to the previous impact, as well as radioisotope content at the beginning, and even they cool more fastly than the bigger body, because we have much more surface with respect to volume. And that's why their activity and their volcanism ended much more before the bigger body. And the volcanism is the way for resurfacing the planet, to give new crust to the planet. So if we want to focus to the small one, we know that actually the moon surface is the moon crust is much more older than the Earth one, just because of this reason. So on the moon, we have the pale gray material are the highlands. We have ages that are up to 4.4 gigayears, and the black part, which are the volcanic origin that have, in any case, much older ages. Most of them, as I said, are before 3.8 gigayears. We have something at 1 gigayears. On the Earth, in which we have this convective south, the plate tectonism, and continuous resurfacing, because it's a bigger planet, we have that the ages of the crust, the main ages of the crust are much younger, with the ocean up to 200 million years. So we can say, and the continent's a little bit older, but most of it's a very young planetary surface. So it means that solar system evolution of the Moon Earth system is retaining for the oldest ages on the Moon. And what is retained on the Moon? I would say it's retaining its early formation that was attributed to an impact with Theia, a body which is with a dimension similar to Mars, that make a complete melting of the silicate shell around the core. And so to the right, we see that from this complete melting at the magma ocean formation, and the magma ocean formation start cooling down and form a first crust, which is actually crust made up of plagioclase, which are minerals of aluminum, calcium rich silicate minerals. And these forming icebergs were continuously destroyed by the continuous impacts through time, up, I would say, to 4.4, 4.3 gigayears. And at that time, we had the possibility to form the first lithosphere, and then the first lava erupted from beneath the lithosphere, but they were destroyed again by the impact. And since we have that the impacts influx were declining through the solar system history, we had the possibility to maintain afterwards the maria, so the outpouring lava there where they formed. And actually they formed thanks to the impacts that destroyed the lithosphere, they alleged the lithosphere, and triggered the partial melting of the mantle and the formation of the lavas. Up to today, in which we have much less impacts and no volcanism. So a beautiful movie that you see here is depicting all the story that I have indicated before. So from the magma ocean moment, you will see the crust start form, the islands, the crust formed by this kind of rocky iceberg made of minerals rich in calcium, aluminum, and silica, and in that time at the formation of the lithosphere. At the beginning, we have a big basin in South Pole Aitken basins at 4.3 gigayears, forming the South Pole of the Moon, and it is the biggest basin that we can find on the Moon, with its 2,500 kilometers of diameter. Then we have all the maria, I would say all the basin that form the near side during the late heavy bombardment, as you see here, that formed between 4 and 3.8 gigayears. And these basins were able to the lithosphere, the rigid lithosphere, I would say creating the plumbing system of magma that was formed from partial melting of the silicate mantle shell and filled up the basins, as you see here, forming the maria dark part that we see on the Moon, that are mainly made of volcanic material basalts. After this stage, we had a declining impacts with still some volcanism, but limited, between 3.8 and 1 billion years, up to our right to the, I would say, the recent times in which the impact declined from 1 gigayear afterwards up to the rate that we see today. So this is actually the evolution of the Moon. And it means that the Moon is dominated by craters of different sizes, from smaller than millimeters up to hundreds of kilometers, with different shapes. So it's a unique impact laboratory all over the solar solar systems, and even the craters themselves can be used for making age determinations. We will go and see them more in detail tomorrow. But the crater density give us an idea of the ages of the units, so that the younger units have small crater per unit area with respect to the older units. Since we went on the moon, we have taken samples, we were able to relate the crater density to the absolute ages, radiometric ages. So we have created, the scientists have created this kind of a chronological curve that is used for making the aging determination of the units on the moon and even on the other planetary body. That's why we had a clear idea of the volcanism that was developed on the moon. And here we have all the volcanic material that has been dating by several hours. And we see that we have from the near size, this 4 gigayear up to very recent, more recent time, up to 1 gigayear, but in very localized places. So it means that on our geological map, the main thing that can be visible are impact material and infilling of volcanic material inside the impact material. And this is an example of the South Pole Aitken Basin, which is, I would say, the geological mapping symphonia by Catherine Poller, which is one of our trainer in the next day, probably the coordinator for the moon mapping. And you see to the right that we have different colors with different materials, as I said before, in which we have a brownish color for older material, older units, and bluish color for much younger units, and the youngest units are in green and in yellow and made mainly by impact, whereas the blue one are impact material together with volcanic material. And this is actually the evidence that what it is, the evolution of the moon, is clearly readable on its surface and can be clearly described by the geological maps. Oh, but in the future, the geological map will be important for the planetary exploration perspective. There are many planned missions on the moon from several nations. We have already seen from the Chinese program already there, but we have also other programs. I want just to cite two of them. So the Artemis program, which aims to, in a cislunar orbit, a space station from which crew can be sent on to the lunar surface for exploration. And in the same way, this Artemis project will be supported by some commercial lunar payload supports and also by the European lunar lander that aims to support crew mission, but also to sustain rover mission situ. And all of that is just becoming a reality in very few years from now. And for these reasons, actually, geological maps are important for them. But if we want to go a little bit further and think about potential stable settlements, we have also to see if it is possible to find resources, in situ resources that can be used for sustained stable settlement, self-sustained stable settlement on the moon. So even if we can see the moon as a kind of deserted place, for sure, we know that the rocks contain oxygens can be extracted, for example, and used for as fuel for rockets. We know that we have solar energy. We have areas that are all illuminated because of the spin axis of the moon, which is almost perpendicular to the elliptical plane. We have the regolith moon, that fine material powder that is formed by the gardening of continuous impact on the surface of the moon. And these powders can be used for shielding future stable settlement or used even for forming landing pad. And finally, we have the possibility to add water. In 2009, it was discovered that the moon has actually a quite could contend, if even not so much on the polar regions in terms of ppm on the surface that has been implanted by the solar, I would say, has been formed by the solar radiation that is able to extract the oxygen, and with the proton form water. And this water migrate toward the poles in areas that are called permanent shadow regions, because, as I said, the axis of the spin axis of the moon is perpendicular less to the elliptical plane. There are places that are always in shadow, and so if the water goes there because of this process or because of the cometary impacts, you know that comets are mainly formed by icy material, that water can be persist and maintained there in the shadow regions. So all this water can be used as in situ source. So in order to have an idea of the resources, as I said before, the sources are one of the main aim, understanding, evaluating the resources are one of the main aim of geological maps. So the use in this kind of geological map is for making very detailed geological maps of landing site, like the one here that we see from ICPAL and another trainer view in the future days that made these beautiful maps of the Apollo 17 sites, and other kind of maps like this one to the right, which is just a part of the northwestern part of Copernicus, in which we see, for example, the different traverse that can be planned for future rover mission, potential rover mission in these sites. So the geological maps are not only a way for understanding and showing the evolution of planetary body, but actual useful tool for their exploration. So going from the moon to the other small planetary body, we can go to Mercury. And Mercury is quite different from the moon, and you can see from this false color composition, you have a very varied surface in terms of color. And since you see different colors, it means different materials. And most of these material are volcanic, and some of rocket volcanic material by impacts, and even some darkish bluer material that could be related to early Mercury. Still, we don't see a clear primordial crust like the highlands of the moon here. So already, for these reasons, I would say that Mercury is quite enigmatic. We have many lava flows that are not clearly visible on the moon, if not mainly contained within the basins on the moon. To the right, we see also a basin, a nice basin, Rembrandt basins, in which we see these impact features all around, some older material, the bluish one, and inside we see the infilling of volcanic material, and all this basin is cut by linear features, as you see here, which is a deformational feature, a thrust, which is another important point of Mercury. So on Mercury, we can see clear features that we call volcanic infilling, volcanic activity. Here to the left, we see beautiful vents within a caloric basin. Here to the right, we see beautiful channels formed by the carving of very fluid lavas that were formed on Mercury in the northern pole. And these lava are very fluid because are very rich in magnesium and are formed by a rock that is called silicate rock, high rich in magnesium, that is called comatite. As far as tectonics is considered, the definition, we see that all the planetary body is covered by these linear features that form, that are showing a general deformation of the planet itself. And these deformation are actually contractional, compressional. They are related to a general contraction of the planet that has been estimated to be 7 kilometers of radius decrease during the last 3.5 giga-years. So the main tectonism on Mercury seems to be related to global contraction, but we have even other processes that could be concurrent with this process, so they can be together, I would say. like tidal despinning. That means that Mercury has a resonant orbit nowadays with the Sun, with 3 rotation around its axis every 2 rotation around the orbits. So a stable spin orbit resonance. And in order to get it, the planet had to spin down. And during the spin down, we have that the planet from a kind of ellipsoidal shape became more spheric shape. And this means that we have deformation that has to account even to this process, together with the general contraction due to the cooling of this small planetary body. We have even seen that some of these features are very old, and probably there could be related even to a very early stage of movements of the plastic mantle, which is in between the core, very big on Mercury, and the rigid lithosphere on the surface. All of this actually is visible on geological maps. This is another beautiful geological map made by your trainers in the next days, by Galluzzi and Guzzetta and Galluzzi here, in which you see that you have many units that are actually imp-related units, like the moon. For example, these yellow are the youngest, and then we have the green, a little bit old, and then the brown, older, even older. But we have many volcanic units either, which are the pinkish one, and many due to the formation of big basins that are the blue ones, okay, that are covered by the pink ones. And all over that units, you may see clearly these linear features that I said before. The linear feature are the formational features that are the tectonism that we had on Mercury. So also in this case, the geological map is telling you the evolution of the planet. But one of the main important points on Mercury is its important metallic core, which is covering up to 42% of the volume of Mercury. And so we have a very thin silicate shell. We had at the beginning 3 main hypotheses explaining this particularity of Mercury with respect to all the other terrestrial, rocky, and iron planets that you see there: Mars, Venus, Earth, and the Moon. And the 3 main processes are related to the closeness of the planet to the Sun, that during the accretion of the planet, since it was very close to the Sun, maybe very volatile materials, but even silicate material were moved in the outer part of the solar system. So the planet, since the beginning, aggregated more metallic iron there with respect to the silicate shells. Or even the planet could have been formed at the beginning, but still, because it was close to the Sun, the silicates were thrown away toward the outer solar system. The last hypothesis is an impact. So we have the planet that was already formed with its silicate shell, outer silicate shell. We had a big impact, and this big impact ejected this part of the silicate shell. So the aggregating planet afterwards was much richer in metallic iron. And all these 3 hypotheses are actually implying a volatile depletion, except some, I would say, some scenarios for the impacts in some cases. But we have volatile depletion. What was discovered in the most recent mission on Mercury, which is the Messenger mission that had flybys in 2018 and ended in the 2015. I don't remember with precisely, but according to this mission, it was possible to see that on Mercury we had a lot of volatiles. And for example, the galactic spectrometer was able to detect potassium that on Mercury has more or less the same content as on the Mars. And potassium is actually a a volatile material. So we have a very volatile material very close to the sun, and this is one of them. And we know that we have many volatiles, even from some volcanic expressions that you see here on these bands. This yellowish material is plastic material. So it's a material formed by explosive volcanism. In order to have explosive volcanism, we need volatiles. And also we have kind of tiny depressions here that are considered to be formed by sublimation of volatile material, and the kind of form called hollows are quite unique in the solar system and are typical of Mercury. And for all these reasons, the next missions that is going to explore the enigma of Mercury is still open. Nevertheless, I will say, nevertheless, we have some answer by messenger, but still the main problems are still open regarding their volcanism, the original primary crust, the volatile presence. All these main questions will be addressed by the Bepi-Colombo mission, whose orbit insertion is foreseen for 2025. So now that we have considered the small bodies that we will cover during this winter school on Tuesday and on Wednesday, we can go on talking about the middle-sized one, which is Mars. We know that Mars is nowadays an ultra-arid cold desert because of the thin atmosphere, so the low pressure at the surface that not allow any liquid water on its surface. So like any kind of desert in the that we know, we have classical dunes and Aeolian deposits formed by the winds, like the dunes. We have even the rocky deserts that are very similar to what we see on the surface of other planets. We may have even some ephemeral reels of brines, solid, I would say, solution of water, but they are highly debated. And this is one of the debated cases which are called recurrent slope linear that forms at the boundary of craters. And the other possible evidences are galleys, but they are very ephemeral eventually, and they do not maintain the liquid surfaces up to the base of a given slope. But if we go back in time, we have the evidences that we have beautiful running water from the southern part of Mars to the northern lowlands of Mars, that are these bluish channels that you see here, and they are the outflow channels are dated back from 3.5 to 2.5 gigayears, and formed by water. They are very deep, up to 2.5 kilometers of depth, and the water discharge is around 1 billion meters per second, and it's several tens meter cubed per second for the biggest rivers on Earth, just to have you an idea of how much water it was there at that time. They have been considered to be events that formed because of some catastrophic moments, since their sources are created by these chaotic terrains that have been attributed to the melting of a icy material underneath the crust, the permafrost, because of a sudden melting due to, for example, nearby impact or to the intrusion. So the intrusion of magma, so the contact between some magma underneath the crust and the permafrost, the ice, that create this huge amount of water that discharge toward the northern part of Mars. And actually, it is the interaction with the water and volcanism which could be very interesting in this period. But if we go back in again, we can see features like these ones. Here to the left, we see the topography of Mars, of a portion of Mars, in which we see the elevated part, which are grayish, and the blue ones that are I would say, the basins, so the lower one. And we see clearly here some dendritic, some clear network or rivers that are going from the upstreams toward the downstream. And the craters that were formed before are actually from the lakes. So we have inlets towards the lakes with infilling of sediment inside them, then the outlets, and again inlet and lake outlets and so forth at that time before 3.5 gigayear. And inside the basin, we see beautiful fan delta, so beautiful delta due to the discharge, if you want, the sedimentation of the material that was transported by the river up to the basins or the craters. So one of the ways for understanding how much water was on Mars, sorry, through time or in any given planet, it's the water global equivalent. So we have to imagine to take all the oceans, lakes of a given planet, forming a kind of thin shell covering all the planets. So at the northern times, the older time of Mars, so before 3.5, 3 gigayear, we had some water global equivalent that could be, according to the estimates, between 1,400 and 550 meter of thickness. Afterwards, during the outflow channel periods, if you want, we had much less water, liquid on the surface, between 100 to 100 meter of thickness. And nowadays, we have no water at all. So the main point is here, why we have so much water at the early time. And one of the reasons is actually to be seen by these big features that we see here that are volcanoes. And here we see a beautiful image of one of the most important volcanic provinces that have the highest volcano in the solar system, which is Olympus Mons that you see here, 25 meter of elevations, and even the largest volcano in the solar system, which is Alba Patera. So these volcanoes, during their activities, make possible ejection gases, replenishing the atmosphere there. So if we think that on Mars we have different volcanic provinces, bigger one, it's actually the Tarsis one that I've shown you before, and the other ones are the Elysium province, the Circumellus, and the Syrtis Major province. All these are volcanic provinces with different volcanic edifices there, and with important coverage of the surface. And if you see colors again, if you see the colors, you see that all these volcanic provinces have this violet to pinkish color. That means, I would say, violet to dark pinkish color. That these volcanic provinces were active in the same time on these planets. So they were injecting a lot of gas at that time. And if we want to compare it with the important volcanic province on the Earth, which are the Siberian Trap, and this is an important volcanic province because when it was forming in the Permian about 270 million years ago, 250 million years ago, we had the complete extinction, I would say almost a complete extinction of the life living on the Earth. So I would say 80% of the life on the water was swept away, and up to 90% of the life on the land were swept away from that unique activity of that unique volcanic provinces on the Earth. So you can imagine how much was the gases that were injected in the early time on Mars between 4 and 3.5 years. And these gases maintain in a more thicker atmosphere with more pressure that allow liquid water to be there. So all the story is well depicted, if you want, on the geological maps. And indeed, we see that On geological maps, we have a geological map like this one, in which we have beautiful example of volcanic edifices with all these concentric features that are typical of the vent close, the caldera part, the collapsed part of the vents of the volcanic edifice with all these lava flows material that are outpoured by harsh amounts here in this case. But also we have a beautiful example of the liquid water running on the surface. So we have a beautiful example here from Pacific in 2008, mapping the flow of an outflow channel, or a beautiful example of a sedimentary infilling of a crater here made by Pondrelli, another professor that is going to tell you how to map geological maps on Mars in the next days. So all these maps actually are showing the story that I have explained to you. Actually, are these maps that have told that story. And that story, as I said, is with the early times, with more volcanic activity, running water like fluvial drainage. Then we have a decreasing of the volcanic activity with the outflow channels that formed during catastrophic event, and then the last time, which is at least from 2.5 or even before gigayears up to date, in which we have this desert environment with no liquid water inside it, and just the ice caps and some frozen CO2 during the winter time that sublimate during the summer. So all this water, now that we know why we had this water at the beginning of Mars history, we can now try to understand where all this water gone. And this is a very nice paper from Scheller et al. 2021 that estimates where molecules of water were gone after these times. And we have three main processes. We have the escape of this water, and then we have the water that remain in the crust, which is the permafrost that I said before. And another loss, in that case, actually, it's not really a loss of water, just the water that it was creating the rocky phreatic part on the early Mars was just freezed there. But lost a lot.
Less than 5 minutes left.
We have, in any case, a lot of water left there. And one of the main possibilities is the crustal hydration, so the hydration of the crust that make water possible on Mars. So with this lot of water, we are sure that now underneath the crust of Mars, we have a permafrost, and underneath the permafrost, we can reach the pressure to have liquid water again. And when we have liquid water, we may have life. And life produces methane that can be trapped on the ice, on some post-crystalline ice, which are called craterate. And when we have destabilization of this craterate, we may have outgases methane. And these methane outgases can be detected and was detected, but we don't know if it is of biological origin, because methane could be even produced by hydration of the crust, as I said before, like this case in which one magnesium and iron-rich rock can be hydrated, and in a CO2-rich environment can form methane again. And we have actually ejection of this methane, and one of the possible sources of this ejection are these mounds that have been here visible on this to the right. So because of this possible life, possible water, we can go back in time. Nowadays we have these maps before and in the late Hesperian, early Amazonian, we may have this kind of picture. Here in the Hesperian, and here probably in Noachian, so in very earlier time. And if we want to compare it with another planet that we know, actually we see that they are very similar. And that's why we have so many missions on on Mars, we have up to 12 missions, I think, in this moment, orbiting or roving on the surface of Mars. And there are planned in the near future other missions like the ExoMars rover that has the main point even to drill, deeply drill on the surface. And again, the Perseverance mission, in which 36 samples of Mars will be collected, then will be taken by other rover to be launched in 2026. This rover has the main aim to bring these samples to a rocket. This rocket will reach an orbital probe that is from European Space Agency, that the duty to collect the samples and send them back again to Earth. And the samples will be afterwards probably starting in 2031. And all of these kind of missions need the same detailed geological maps that shown you before. So in conclusion, I would say that we may say that the geological maps actually define function of the planetary bodies and the geological environment. So that's Moon, we have a beautiful interplay between impact processing and volcanism. On Mercury, we have a beautiful interplay between impact processing and volcanism, but we have also global relevant widespread contraction, tectonism, deformation. And on Mars, we have all possible environments: volcanic, tectonic, fluvial, even glacial and Aeolian environments to be studied. And we will focus mainly on fluvial one. So another point is that planetary missions will dramatically grow in the next decade. And the third point is that planetary geological maps are pivotal for any planetary science investigation in the future, and any planetary exploration strategy, including the crewed exploration or future stable settlements. So thank you for the attention.